method. Okay, so let me now share my screen. Okay, I'm sharing my screen now. So hopefully you can see my screen. Here's what I'm sharing it. Here I've I'll zoom in a bit. Okay, so we've got three different approaches. So this is the point clarification method. And again, I'm trying to, oh, maybe this is kind of cool. I can see this as well. So I'm trying to solve this. So we're trying to solve this this differential equation here, right? Okay, so we've got our trial function here that I wrote out, and this is second derivative. This is in MathCAD, so you can solve it in MathCAD. And then you get the residual here, and I've written it in terms of alpha 1, alpha 2, and x. And so then with the point collocation, I can choose 2 points where I've chosen x1 and x2. That will give two residual equations at 2 different points, right? And then I can solve for alpha 1 and alpha 2. And so this is solving for the first one, solving for the second one, and then it gives me alpha 1 is equal to this and alpha 2 is equal to this. Okay. So then based on point collocation, this is our solution in here. Okay. Now, and then this is the exact solution here. So if we compare the two, this is the error percentage. So I've taken the exact minus the point collocation divided by the exact. So it's pretty good. It's less than 3.3%. And if we make a plot of the two solutions, you can't really see the error. But there is some error. Okay. Then, second approach is the integrated least squared method. We've got the trial function, take the derivative of the trial function, okay. Then we subtract the trial function into the differential, we get this residual. Now, we take the derivative of the residual, that's the approach used to in the weighted residual. Take the derivative of the residual for the two unknowns, alpha 3 and alpha 4. And then we put it into the integration. So as you can see here, you take the derivative of the residual, multiply it by residual, and then integrate it from 0 to 1. And then this is what you get out, these two terms here. You solve for alpha 1 and alpha 2. Sorry, I'm calling it alpha 3 and alpha 4 to make it differentiate the coefficients from the point collocation. We solve for the two unknowns, which are called alpha 3 and alpha 4, and then this is what we get out. So you can see the coefficients are different, and this is the exact solution. And then we compare, and you can see least squared is better than the point collocation. There's still error, but the least squared is closer. Okay, third approach, the Galerkin. So for the Galerkin, we have the trial function, got the residual. So in the Galerkin, we multiply the weighting function. So this is the weighting function. This is the so this is the weighting function. We've got two weighting functions, this one and this one, in the brackets. We multiply the weighting function first one by the residual, and similarly we multiply the second weighting function by the residual, and integrate, and then this is what comes out. Two terms. We solve for the two unknowns, which are called alpha 5 and alpha 6. And so we get alpha 5 and alpha 6, these two. And then we say substitute in. This is the trial function. This is the trial function. Compare the solution based on the Glerkin method function with the other two. And so comparing with the exact. And this is what we get. The black one is the Glerkin. And then this is the residual for 3. So the Glerkin turns out to have the so in this plot here, I compare them. This is a better way of showing it. We've got the exact, and we minus the point collocation answer, right? That's what so the red one is the point collocation. The black one is the least squared, and the blue one is the Glerkin. And so you can see the error difference for the Glerkin is the lowest. So the Glerkin is the most used approach because it gets you in general the least error. Okay. So how does this relate to the finite element method? There's a lot of lectures on that online. That I'll just run through a couple of points here. So if we have a 2D problem that we want to solve using the finite element method, then we want to ideally use the you want to go with the magnetic vector potential because you only have to solve one unknown. Okay, so we have this we have this equation here for the problem where I've just got the current source and the differential equation, and so then you've got this magnetic vector potential here. This is what we're trying to solve for in two degrees of freedom. So the AZ, there's a trial function in terms of x and y. See, and it's a trial function, and so you'd substitute that in to the differential equation you're trying to solve, and then you get a residual out. So you'd get out an error. Right? This will be an error. It won't be 0 unless you've got the exact answer. So R will be greater than 0. And so then you multiply this residual by a weighting function and integrate over the problem domain. So instead of being 1D, it's 2D. So you'd have the residual. You multiply it by the weighting function, and then you integrate it over the problem domain. And so then your problem boils down to solving a differential equation where you integrate it over the problem domain, and you use trial functions to solve. And you force this to equal 0. So this is the basis of the finite element method, and so you end up breaking down the problem into many triangles, and each one, it turns out, then you evaluate this integral over each triangle, try to minimize the error in each one, and so that's the basis of the finite element method. So there's a whole lot of more steps in derivation that take a couple of days to present all of that material. But I wanted to give a flavor for what goes on inside the finite element analysis program. But to get a better appreciation, you need to go over some more of the lectures they're provided on the CUSP website. Let me go over a couple more things. If you have any questions, shout out. Talk it out. So what I've done in the past is I have students solve this problem here. After giving more theory, you have to solve a problem which involves a 2D model shown here. We're made up of two different regions. You've got a magnetic region, omega 1, and an air region, omega 2. And we apply a magnetic vector potential on one side of 0, and then on the other side, the magnetic vector potential is 1 times 10 to the minus 3. And as I talked about this morning, if you have a difference in magnetic vector potential between 2 points in 2D, it creates a flux flowing down. So then what if you set this vector potential different on each side, there must be a flux being created that flows down from the top to the bottom. And so the students have to solve this using the finite element analysis code that they develop themselves with this geometry, and then calculate the energy in the air gap. An example of a student's work somewhere around here. So this is an example of one. In this the triangles are made up of in a grid pattern as shown here. They did two different numbers of elements, So you break down the problem into thousands of elements, and then you solve using matrix theory the solution. This shows you the vector potential lines for the solution, and you can see that the field wants to go around and stay in the magnetic region because it doesn't want to go in the air gap, and so that that the field flows down. And so then if you increase the number of elements, you can calculate the energy in the air region. So I guess students calculate that from evaluating the magnetic flux density in the air gap, taking the derivative of the vector potential and then integrating over the area. And so that's an example. Another example of problems that are solved are is this, for example, here. That this is using the winding function analysis, and this is given on the CUSP website. This is a finite element analysis model where you've got the conductors and the magnets, and you have to solve for the air gap and look at the harmonics. And so this is the mesh. It's not optimized or anything. It's just an example one. And so the students have to. The mesh is not as limited with the student version of JMAG that's used. This shows an example of the plot, and so the students calculate the harmonics, and then they look at the they then also have to look at the FEA analysis for the winding functions. So this is an example of the comparison between the winding function with fractional slots and concentrated. And you see that the magnitude significantly decreased in this example, but the higher order harmonics are decreased, although the third harmonic is still large. Okay, and so that's basically all I want to show here. I think I've so what I was doing here was I didn't stop at the 1 o'clock. We did the interruption of the weighted residual. I went over the point collocation, least squared, and Galerkin. I then gave an example of a more realistic example of solution. And then I've just gone over the finite element MATLAB problem that is provided in the class that I have taught, and outlined the approach using the Galerkin method that you'd use to solve it. There's a whole lot of steps. So there's 1, 2, 3, 4, 5 additional lectures that can continue on from this point, that you're welcome to look over. They go over in steps the solution to the finite element problem, maybe one more thing. If you want to, if anyone's still there, let me just briefly talk about other books that might be of interest to you. If you want to dig further into this topic, just bear with me. I've just got to find the course material handout. Can't find it when you need it. Okay, here we go. Let me share my screen again. Okay, so in here, there's a number of books that are quite good. This one here is on the numerical modeling basis. This one is on the design of rotating machines, sometimes somewhat hard to follow in places. I believe I've explained a fair chunk of this book in different aspects. This Fitzgerald and Kingsley, this is an older version that talks about electric machines, induction machines, DC machines, synchronous machines. It has a nice introduction onto actuators. This one goes into more detail just on the permanent magnet modeling. I think I present permanent magnet modeling in perhaps more detail than some of these other ones, actually, in my opinion. This one's another numerical modeling of electric machines. No, sorry, not electric machines. This is numerical modeling of yeah. So these are a good range of books. I believe these are listed on the CUSP website, so you can take a look on there. Okay, that's all I have. I'm going to stop sharing, and okay, I'm gonna finish now. And I hope someone's learned at least a little bit from this presentation, and good luck with your work. And if you have any questions, you're welcome to connect with me via my email address. Okay, thanks very much. Bye-bye.